Hello, today I will present the case of study of bungee jumping. Bungee jumping has an interest origin. It comes from a ritual in Pentecost Island, which later inspired Chris Baker in 1979 to develop the modern sport in England. Today, millions of jumpers have been performed worldwide safely thanks to the application of physics and mathematics. To model the motion of a bungee jump, we divide into two main phases. The first one is free fail, which happens until the rope is fully stretched, and the second one begins when the rope acts like an elastic spring, following Hooke's law. Each phase requires different equations to describe the jumper's motion. In the first phase, the only force acting on the jumper is gravity. Using Newton's second law, we get the following system. The acceleration is equal to minus g, and the velocity is minus g times time, plus the initial velocity, and the position is the initial height, minus 1/2 g gt squared, plus the initial velocity times t. Since the jump starts from rest, the initial velocity is 0. We now introduce the rope length, represented as L0. From the position equation, we can calculate the time it takes to reach the maximum extension point of the rope. This gives us the expression t equals the square root of 2L0 over g. Finally, we calculate the velocity at the instant, which is equal to the square root of 2g times L0. This velocity will serve as the initial velocity for the second phase. In the second phase, the rope starts to stretch and behaves like a spring. The elastic force is given by Hooke's law. F is equal chi and g. By combining this with Newton's second law, we obtain the differential equation d squared g over d t squared plus k over m times n over times e equals g. We rewrite the equation in standard form, d squared g over dt squared plus omega squared e equals g, where omega squared is equal to k over m. This representation allows us to solve the equation more easily. To solve the system, we separate the solution into two parts. The homogeneous solution is c, 1 times cosine of omega t, plus c 2 times sine of omega t. The particular solution is minus mg over k. The complete solution is the sum of these two parts. We now apply the initial condition. At time equals 0, the position is 0. This gives us c1 equals mg over k. At the time equals 0, the initial velocity is equal to the final velocity of the free fall, which we already calculated. Substituting, we find the c2 equals v0 over omega. Finally, the complete equation of the system is g of t equals mg over k times cosine of omega t plus v0 over omega times sine of omega t minus mg over k. This function describes the oscillation motion of the jumper after the rope begins to stretch. Now let us analyze an example with a mass of 90 kilograms, of a spring constant of 900 newtons per meter, and a rope length of 15 meters. With these values, the maximum elongation of the rope is 7.3 meters, which means the total fall is 22.3 meters. Now let's compare this with my own case. With a weight of 72 kilograms, the velocity at the end of the tree fall is 17.15 meters per second. And in this case, the rope elongation only 5.7 meters, and the total fall is 20.7 meters. This means that with my lower weight, the stress on the rope is reduced, making the motion more controlled. In conclusion, the final velocity at the end of the free fall depends only on the rope length, not on the mass of the jumper. However, the elongation of the rope depends directly on the mass. This shows why personalized calculations are essential. A lighter jumper will experience less stress on the rope and therefore a safer jump. This case study proves how mathematics can help ensure safety in extreme sports like bungee jump.